Welcome to. All right. Hello, everyone. Welcome to today's AFMS seminar series. It's my pleasure to introduce today's speaker, Professor Thomas Pähtz. Thomas is a distinguished professor at the Sediment and Environmental Fluid Mechanics Lab, Ocean College, Zhejiang University, China. He completed his PhD at ETH Zurich in Switzerland, and he subsequently took up academic position at Zhejiang University. Professor Pähtz research focused mainly on sediment transport and groundwater flows and their relation to geophysical phenomena, including the formation of ripples and dunes. Today, he's going to talk about the scaling behavior of wind-blown sand and fluvial bedload transport. Thank you, Thomas.
Okay. I'll share my screen first. Okay. So the topic is wind-blown sand and fluvial bedload. And what I'm going to present today is from several authors, but 95% of what I present is from me and Lorenzo Duran. And okay, so the wind-blown sand and fluvial bedload are two examples for what I call non-suspended sediment transport. So it means you have a flow, for example, wind or water, and it flows along a surface and it drives the motion of the surface particles, and usually in the form of rolling, sliding, or saltation, which is when particles lift and come back. So non-suspended means the particles remain in regular contact with a bad surface, and this is different from the suspended regime, where I will show you a video. So suspended transport would, sediment transport would, for example, be a dust storm, as in this video. I hope you can see it. So this is not what I'm talking about. So I talk about non-suspended sediment transport, and I will show you a few examples. So here you can see like water, bedload transport by water in a river or in a small stream. Then you have this also in at the coast by wind. So here you can see the wind is coming from above, and you can see those streamers, which are basically non-suspended sand transport by wind. Okay. And then you also study this in laboratory, for example, in wind tunnels. Here in this video, we have wind blowing from the left, and you can see the particles moving. And in the case of wind, so the typical transport height of particles, so how much do they detach from the bad surface, is 100 diameters. So many particles have maybe around 10 diameters, and there are also some particles that can have 100 or even 1,000 diameters. Okay, and that's very different from the fluvial case, bedload in water, where the transport happens usually very, very close to the surface. So let's look at this flume. You can see transport happening close to the surface, very close. So I show this video also for another reason, because when you look at all the cranes, including the ones at the surface, which are at the moment not moving, but in a few seconds, the time scale of the video will accelerate. And then you will see that not just the surface is moving, actually the entire bed is moving over long enough time scales. Okay? So when I say non-suspended sediment transport, this includes the regime where everything moves, including the salt at the surface, which is what the people call creeping. So why am I interested in non-suspended sediment transport? Because it is one of the most important drivers of planetary landscape evolution. So you can see here, for example, on the right, it's an ocean, and you see at the coast those underwater ripples. So the transport of sediment by water causes the formation of those structures. For here, that is snow. So you have wind-blown transport of snow or ice particles, and they create also some kind of structures, and these structures are commonly referred to as bed forms, and the two most well-known ones are ripples and dunes. So these are ripples here and here, and here that would be transport. This would be one big dune. It's not a particularly good picture though, but this would be sand transport along a big dune. So dunes can be of orders of 100 meters to kilometers. Ripples are usually smaller. You don't just have this on Earth, you also have it on other planets in the solar system, for example, on Mars. This one is an image taken by the Curiosity rover of the Mars surface. And here you can see different kind of ripples. Okay? This is another image, also of the Mars surface, but from a satellite. And here you can see a big dune, that's the middle thing, the middle structure, and also many, many smaller ripples. And not just on Mars, potentially, you also have these things on Pluto. So in 2015, there was the space probe called New Horizons passing by Pluto, and it made pictures of the surface. And some researchers looked at these pictures and saw structures, and they marked these structures in this here as these black things, and they believe these are dunes forming due to wind, due to the transport of ice particles by wind. And here I have to mention is that if this were true, as these researchers claim, it would be quite astonishing because the air pressure on Pluto is about 100,000th of that on Earth. And on Mars, it's 100th of that on Earth, but here it's 100,000. There's basically almost no air. And so if these really formed on the present day Pluto by the action of wind, that would be quite astonishing. I personally doubt that, but that's not important for this talk. So in order to predict these processes, how do dunes and ripples and other bed forms form and evolve, one of the most important things one has to understand is the so-called sediment transport rate. And especially as a first step, the sediment transport rate under equilibrium conditions. So suppose you have some kind of channel here, okay, and there is a flow like wind or water driving the motion of the cranes. And at the end of this channel, or wind tunnel or whatever, you have a container and it collects the particles. So what you measure now is how much mass is collected in this container per unit time and unit width of the channel. And that would be the sediment transport rate. When you have equilibrium conditions, then this first measure here is the same as the second measure, which would be the total extreme-wise momentum of all particles per unit area of the bed, so width times length. So what I have been doing since around 2013, I have been trying to understand the scaling behavior of the sediment transport rate. And I wanted to be able to derive a theory or at least some kind of model that is able to precisely predict the transport rate across environmental conditions. So not just on Earth where we have measurements, but also on Mars and other planets. So, and when it comes to sediment transport rate, I will start with the historical approach. So what have most people done in the past to derive expressions? They haven't done it exactly like I do here. It's more like a summary. This kind of logic will lead to a structure of the equations which you can find in almost all published scaling laws of the sediment transport rate. So the idea is we have crane parameters, okay? So this would be the particle density, crane diameter, assuming spherical cranes, they have the diameter only, and then the sediment transport rate. And then you have environmental parameters, such as the flow density, the density of the fluid, like the air, the kinematic fluid viscosity, the bad shear stress, the bad shear velocity, and of course the gravity. So the assumption, essentially the assumption behind most models or theories published in the literature is that in equilibrium, the sediment transport rate is a function of only environmental parameters. In this case, this would be Q as a function of OF, UF, U star, and G. So the first small improvement of this assumption is the following. So when you think of particles submerged in water, they will essentially never feel gravity alone. They will always feel it together with buoyancy. So what you do is, as a first modification of this law, you replace the G, the gravity constant, by a G tilde, which subtracts the effect of buoyancy. So now you look at the submerged rate. So the second thing, what people usually do, they consider a logarithmic profile. So a logarithmic wind or water mean velocity profile. And this is valid as once the particle Reynolds number is sufficiently large. At least when you are not too close to the bed in the case of a viscous sublayer. Okay, and in this law, essentially the viscosity doesn't matter anymore. So when you assume a law like this, then the viscosity wouldn't matter as much anymore. It would still be in the roughness, potentially, but it's only logarithmic dependency. So this means, second modification, we assume that the viscosity doesn't matter. So what we have now is we have dimensional analysis. So we have one quantity, which involves units kilogram, meter, second, depends on three natural parameters. And there's only one way to combine this. So the Q is proportional with the proportionality constant CQ to OF U star power 3 divided by G tilde. So now they know this law, they know is not exact, cannot exactly be right. Why? Because it predicts that Q only vanishes when the U star goes to 0. However, they know that at least most of sediment transport vanishes once you reach a certain threshold value, which I call U star T for threshold. So this leads to the following modification, where I say, okay, the proportionality constant CQ is not a constant, but it actually depends on the distance from this threshold, dimensionless distance from this threshold, U star divided by U star T, with a condition that at CQ at 1 is approximately 0. So when you do this, and now you divide by these natural units, OP, the square root of S tilde GD. I will explain in a moment why, okay? Then you end up in this dimensionless law, where you have dimensionless sediment transport rate is proportional to this thing is called the Shields number. Shields number power 3 over 2. And the proportionality constant depends on the distance from this threshold. So in this equation, I have used another definition, S, which is the particle fluid density ratio. And yeah, so why is this kind of rescaling? Why do we do that? Because the Shields number can also be expressed as via the shear stress. And here you have like a ratio between tau d square, which is in some kind of measure of the tangential force applied on the bed surface. And this one here would be a measure for the normal, for the resisting force in the normal direction. And so when you have tangential divided by normal force on cranes, this is also called a friction coefficient. So the reason we rescale in that way is because the Shields number somehow has the physical meaning in some sense as a friction coefficient, and especially there is usually when we, for example, have an object sliding down a plane, there is a critical angle. And when we, in analogy, we have a critical Shields number, which would be the sliding friction coefficient in analogy of the object sliding down the plane. So that's the reason we rescale in exactly that way. Okay? So all these, so based on this dimensional analysis, so we have that the dimensional sediment transport rate is Shields number, power 3/2, times a factor that depends on the relative distance from the threshold. So, and here is it that almost all published equations in the literature have exactly this shape. And these are just a few examples. I could give you probably 50 to 100 more. Okay. So this is, from my perspective, a summary of what people basically have done when they modeled sediment transport in the past. They have assumed that the flow drives the motion. So particle motion, so the particle motion is only a function of the flow. That's very roughly saying what they did. And now I will do something different. Okay? So what I'm going to present to you is what I came up over many years as a more, in my opinion, better approach to model sediment transport. So the method I used is as follows. I used DEM, discrete element method, of advanced simulations, coupled for a large range of conditions. So the conditions are given by the density ratio, ranging from 1.1 to 10 to the power of 7. So this would 1.1 would be typical for particle transport in water, and about 2,000 would be typical for wind-blown sand on Earth, and 10 to the power of 7 would be wind-blown sand on Pluto. So what we did is we simulated all those conditions, and we got a lot of data. And then we tried to understand these data based on physical modeling. And once we have done that, we came up with a physical model, and then we compare this physical model not just to these numerical data, but also to experiments where they exist. They usually exist only on Earth. Okay? So here I will show you a few videos, 2 videos. So here that would be a DEM AFMS simulation of wind-blown sand. So what you can see here is only a quarter of the simulation length. So you have wind blowing from the left, and the color is the wind velocity. And you see the particles, when they impacted the bed, a lot of strange things happening, a lot of other particles may be ejected. That's very typical for wind-blown sand. Okay. So another video would be fluvial transport, Bedload. So something like sand and water. And here everything moves much closer. And these are 2D simulations, by the way. So, yeah. Okay. So we have now imagine we have all these data produced. I will not go into details about the details of the numerical model. You can ask me this in the end if we have time. But now let's imagine we have all this data, and what did I come up with over the years to model it? So first, I introduce one quantity, that's the transport load. So essentially, when you have particles moving and they get an upper index I, so we sum over the masses of all particles. Okay? but only those that are located above the bed surface. The bed surface is the interface between the wind or the water and the granular bed, and we have a definition for that, but that's not important. So we sum over all the masses of all the particles above the surface, average over time, and divide by the area, so per unit area. That's the area of the simulation domain. Okay? That would be what we define a transport load. On the other hand, the transport rate is what I showed you before, the total streamwise momentum of all particles, not just those above the surface, but of all particles, averaged over time and also per unit area. So the first modeling step is to say, okay, the total momentum of all particles per unit area can be approximated as the total streamwise momentum of only particles moving above the bed surface. And by the way, we confirmed this, this assumption. It's usually correct to a degree of, at the very least, 80%. In the case of Windblown, then typically 99% for our particular definition of the bed surface. So once we can do this, we can replace the right-hand side here, this one, by the transport load times the average velocity. So this is kind of another way of saying this is the transport load times the average streamwise velocity of transported particles above the bed surface. So this is basically here done for the mass, here done for the streamwise momentum, and you can do this also for vertical momentum energy. So in the case of vertical momentum, what we get is the total vertical momentum is 0. Why is that? Because we are looking at equilibrium, and in equilibrium, as many particles on average are moving up as they are moving down. And so the mean vertical velocity is 0. Otherwise, it wouldn't be in equilibrium because the whole system would move up or down. So energy is clear. And then there is something similar to energy, which I call EXZ, where we replace the velocity vector square by Vx Vz. And then you get, this is a mean of m Vx Vz. So you have a Vx Vz. These are particle velocities, right? So mean. And because the mean vertical velocity is 0, this is equal to the fluctuation Vx Vz. So in a sense, this is a fluctuation energy-like quantity. Not exactly an energy, but an energy-like because it's Vx Vz instead of the velocity square. Okay. Now, this becomes now important because we can write down almost, not almost, exactly without any approximation, we can write down a law for the production of EXZ, and the dissipation is equal to the dissipation rate of EXZ. Okay, and let's start with this equation. So when we look at the sum over all these energies of all particles, so 1/2 m Vxi Vzi, and we take the time derivative, then what we get is this is the sum of all forces times velocity, and these brackets here mean symmetrization. So it means Fx Vz plus Fz Vx divided by 2. So then you have these forces, and you can separate these forces into different contributions. One from the gravity without buoyancy, G tilde here. Another one from particle-particle contacts when they collide, for example. And a third one from fluid forces, here just called drag. So fluid forces. So now we take the average of this equation, okay? Average over time. And in average, in equilibrium, there is nothing changing in time. So this left term is basically 0. So if this term is 0, or this term is 0, then we can express this is equal to minus this minus this. So the red is equal to the minus the two blue terms. And one can show, and that is also exact, there's no approximation at the very moment, that this equation rearranged is somehow the sediment transport rate. And here the clue terms are the dissipation of this EXZ energy by C contacts and D Trag. Okay. So, and now this is up to here, everything is exact. And now the actual modeling starts. And before I say do this, I will say that this way of modeling sediment transport is, I think I'm the only one doing it that way. Everyone else is always going via the flow, and I'm trying to go via the granular mechanics. So now, what I now assume is, so here's exact, and now we do assumptions. We are saying, okay, the dissipation rate by contacts has basically two components. Contacts between two cranes in transport, G, and contacts is from crane/bed collisions. So we are only interested in the effect, so in the effect as a function of m star. Okay? So the dissipation rate by crane bed collisions will be proportional to the number of crane bed collisions. So this will give us that the m star dependency should just, for this reason, just be m star power of 1. Because m star has we can show that m star is essentially also the number of particles in motion. So this would be number particle 1. For crane-crane collisions, so we have two cranes in transport colliding. They have to be at the same place, so probability is the number of particles squared we will get here. That's why you get m squared. And for the Trag, the dissipation by Trag is essentially also proportionate to the number of particles that are moving, so m star power 1. These coefficients, AC, BC, AD, we don't know anything about them, except that they are not supposed to depend on m star. They can depend on anything else, but they're not supposed to depend on m star. So what we have done here, we have extracted the m star dependence based on these assumptions. Okay? So now we combine these equations and put them into this equation. There will be a new constant C. Doesn't really matter. We will talk about them later. And so we combine it, put it in, and what we get is Q star is equal to one constant C times m star times 1 plus another constant times m star. So now, when we divide Q star by m star, we get the average streamwise velocity, approximately. But I showed you that this is before, that this is, as I said, this is actually good. So from this means this is the average velocity of the transported particles. Now we can look at the special case of the m star going to 0, the number of transported particles going to 0. That is what I call threshold conditions. Okay? So when the m star goes to 0, then the velocity of moving particles will be the velocity at the threshold. And from this, I extract that this constant C is the streamwise particle velocity at the threshold. By the way, also stars here mean dimensionless. So this is all dimensionless. So we end up with this equation. And this equation is now the equation we are going to test with the simulation data. So what you can see here is on the right-hand side, the plot, and many different conditions, different density ratios, and also different Galileo numbers, but I haven't decoded them in this legend. So I only show you the value of the density ratio. And it ranges from 2.65 to 10 to the power of 7. And what we find is that this equation is actually very well obeyed over all these conditions with a constant value of Cm of 1.7 if this dimensionless number, this GA squared S, is sufficiently large. And this number is essentially a measure for the effects of crane inertia relative to viscous forcing. So what is surprising about this is that this constant Cm, which can actually depend on anything but m star, is found to be a universal constant in the simulations. And up to today, we don't have an explanation why that is. Okay. So now what, in order to have an expression for Q star, we need expressions for the two unknowns, m star and Vx velocity at the threshold. And here I will not show you the derivation, I will just explain it with words. So the m star is basically the mass or the number of transported particles, above the bed surface. So in a sense, this is the weight of the particles above the bed surface. This is in a sense the pressure, the particle pressure at the surface. And what we are relating is the particle pressure at the surface, we are relating it to the particle shear stress at the surface, and this involves a friction coefficient μ. And the particle shear stress is by virtue of momentum conservation, so the mixture shear stress, theta, and the remaining shear stress of the flow at the surface. So when you go from above the sediment transport layer to the bed surface, so there will be particles coming that will subtract momentum from the flow, and the flow shear stress will become smaller and smaller and smaller. And if we are saying it goes to this threshold, it will be almost exactly equal to the threshold, so that the system is barely able to continue to move. Okay. And what we find is, roughly at least, that all these conditions can be described by roughly a constant value of the friction coefficient. So number 3 would be the streamwise velocity at the threshold. And here we are using the same kind of idea. We also just in words. So we assume that a particle continuously bounces along a flat bed according to some kind of bouncing rules, which are basically rebounds. Okay? And when we do this, we can ask the question, what is the smallest flow velocity that allows such a continuous bouncing motion? And this smallest velocity is what we define as a threshold. And from this analysis, from getting this threshold from this kind of very simple picture, we get that the threshold velocity, we get as well that the threshold velocity, the streamwise particle velocity at the threshold, is equal to 5 times the square root of this Shields number, the critical Shields number. And we can see, as long as this dimensionless number here is sufficiently large, this is actually a good approximation of the data. And this dimensionless number means that the particles are actually really moving in a log layer, because in order to derive this equation, we needed to assume a log layer. And left from this would be viscous sublayer influence. Okay. So now we can put these two equations in and get to a final equation. That would be this one. And then we can compare this final equation, not with some numerical simulations, what we have done, but now we compare it with actual measurements. And at this stage, the only thing that we kind of fit is this value theta t. Okay? So what you see here on the right-hand side are measurements for wind-blown sand on Earth. And what I would like to point out is, when we published this equation, these triangle measurements did not yet exist. So this was published after we published our equation. And our equation was basically describing this data up to about here, and then I made a prediction. And this prediction was effectively confirmed by these measurements which came after our equation was published. So this is not just describing existing data. This made a prediction that turned out to be true. And from viewpoint of scientific method, this is a very big support for the theory. So this would be windblown sand. We also have agreement with existing data of windblown snow, and also with data of fluvial bedloads. In all these cases, the theta T is, for now, fitted. Okay? And here, when we apply to fluvial bedload, we had to take into account the bad slope angle, which I didn't talk about so far. Okay, this is alpha. So let me summarize this part. So we have a unified relation that unifies sediment transport in water, in air, and across many environments in air, actually. Yeah? And what's important is this relation is not of the standard form, which comes from the dimensional analysis I showed you before. It's different. So what's different? The red term is different. This red term does not obey this structure. The left one, yes, this part does, but the red term does not. And the red term, the CM, comes from those crane collisions. Essentially, that is, this red term is the ratio between the frequency of crane and crane bed collisions. And what it predicts is, so when we have intense conditions, with many crane collisions, then this term becomes significant, and then the sediment transport rate would scale with the Shields number square. And this is actually well known for sheet flow. People have long known that the actual scaling is Shields number square and not Shields number power 3/2 like here. So there's more. When we approximate this plus this, it's like when we think it's an arithmetic average, and we approximate it by a geometric average. And this is a good approximation as long as A and B, the ratio of A and B is not like larger than 10 or smaller than 0.1. Then we get a relationship like this, and this has this theta minus theta T power 3/2. And this was the very standard scaling they have been using for about 100 years. For engineers have been using this, physicists have been using this to estimate the bad load transport rate. So in the case of bad load, we can do this approximation, more or less, for a very large range of Shields numbers. Okay. So what I just showed you up to here was derived over many papers. The two most important ones are those, and one of them is got a highlight in physical reflectors. Okay. What I show you now, so this was a topic finished, and what I show you now is the model I just presented to you. We improved on it recently, and this is what I'm going to show you now. So this was the model, how it is at the moment. And now so far we have actually treated grains as spherical, and even when we compared with measurements of non-spherical grains, we treated those measurements as if they were spherical grains. Okay? But now we are saying, okay, now we take actually into account the grain shape. When we do this, in order to, the logic that led to these equations has to satisfy that M star has a meaning of a transported particle number. And because particles tend to, in Bedload transport, I'm talking about Bedload transport here only, fluvial Bedload, because particles in fluvial Bedload tend to align their longest two axes with parallel to the bed, this will lead to that we have to replace D, the crane diameter, by the C, which is the shortest axis. And so all the non-dimensionalization done by D is now done by C. But then the equations would be, the logic behind these equations would be the same, and it should still be okay. That's improvement number one. Improvement number two, before I was just talking about a friction law. where we had here mu b power minus 1. Well, now we take into account bad slopes and also lift forces on particles, which we haven't taken into account before. Lift forces are forces that are, when the flow is streamwise, that act normal to the flow direction. So then, straightforward analysis of the same thing will give us this. So there's actually, physically speaking, not much difference, except that we consider a few more things, bad slope and lift forces. The third one is this bad friction coefficient mu b is now linked to particle shape. What do I mean by that? So we assume that this bad friction coefficient is proportional to the tangents of the angle of repose of the grain material, and spherical particles will have a much smaller angle, not much, will have a smaller angle of repose than non-spherical particles, or very angular particles can have a very large angle of repose. Okay? So why proportional and not equal? Because we are talking about the bad surface, and the bad surface relative to the bulk of the granular material will have a higher shear resistance. And this is because when bad load transport occurs, you can believe that you can think of it, the particles are detaching from the bed, and they will find more stable resting places. And this is a process that goes on and on and on. The particles will, so the bed surface will tend towards a more and more and more stable state, which means the shear resistance will increase. However, we assume that the increase will still sort of have a memory of the original state of the shear resistance of the bulk. And so the memory is sort of, we say, this proportion is a proportional, these two, the bed and the bulk, but the proportionality is a constant, which is larger than 1. And the fourth improvement would actually be the predicting the threshold. So before, in the plots I showed you, where the threshold was fitted, was just adjusted to a given data set. Now the threshold is actually predicted. And here, this is a standard model. What's important about this equation is it also depends on this bad friction coefficient and on the angle. And it depends on the settling dimension, the settling velocity of grains. So when we have a given grain shape, we can measure how long does this grain take to settle. And it also depends on the grain shape, which is the C divided by square root AV. This is known as a Corey shape factor. And what this essentially does is we estimate the drag coefficient of spheres falling vertically. And this factor will essentially translate this vertical drag into a streamwise drag by taking into account the projected area will vary. So particles settling down vertically will expose their largest projected area to the flow. And so there will be changes when you consider it in the streamwise direction. And this is what the shape factor does. So that you don't need to understand the details, just understand this depends on the settling velocity and on the shape of the grains. So, and with all this, we now test this improved model with a lot of independent data, including our own, but also including many, many data from different studies. So we have the criterion we use for testing this, that the studies, the experiments or numerical simulations had to control for grain shape. And there are not many in the literature that do that. They had to control for grain shape, and they have to provide us the values of the settling velocity and of the angle of repose. Okay? That was a requirement, and we looked for all data sets we could find for that. And these include experiments, grain resolved CFD DM simulation, so where the flow around a particle is resolved, so we don't have to introduce empirical fluid drag or fluid lift forces. And then unresolved simulations as well, where we have some empirical measure for fluid drag forces or fluid lift forces. So the data we use to test this model include conditions where the channel flow, these are channel flows, open channel flows, so where the channel flow height and widths vary a lot. So the width varies from just 2 diameters. Imagine a channel which is just 2 diameters wide to basically infinity, and a height which is just 2 diameter height to basically infinity. And especially some of these simulations had width to height ratio, not the simulation, some of the experiments had a width to height ratio of just 0.1. And so in order to test our model, we also had to derive a new sidewall correction method, because existing sidewall correction methods for this kind of very, very narrow channels didn't exist. But I'm not talking about that. I just say we had also derived a new sidewall correction method. So these data sets include crane shapes, spheres, ellipsoids, ships, gravel, prisms, cylinders, lenses, rods, a large range of bed slopes from 0 to, this is a very large slope angle, much larger than you would typically get even in mountain streams, and a large range of flow strengths. So what we achieved is we were able to describe all these data from all these different methods and different conditions within almost all this data within a factor of just 1.3 by using 3 values of these model constants, which I just introduced. The RB for the bed friction relative to surface friction, and these parameters related to the track law, the CT, and the lift to track ratio. And here on the left-hand side, just that you see, on the left-hand side is the data of Q star divided as a function of theta to see how much it spreads. These different data really, really spread a lot. And yet, after applying the model, they are very, very close together, and we can predict them within just a factor of 1.3. This would also be my takeaway. We actually have, from this improvement, we have managed to largely diminish bad load variability, at least for the cases we consider, which are equilibrium flows or steady flows over flat beds at short time scales. And previously, there was really a large variability. Typically, a variability from an order of magnitude is possible from study to study, even for the so-called same conditions. And what we find is that most of the variability comes from sidewall and crane shape effects. So there is the main limitation of this bad load model is that it has to, the bad particles have to be sufficiently large. So this number must still be larger than about 80, which is particle size must be larger than approximately 1 millimeter. So I'm mentioning this because Amman has published data in 2017, which I couldn't use because they were only 0.5 millimeter large particles. So the paper on this is still in preparation. So now another improvement, but it's a different topic now. So this was an improvement particularly for Fluvial Bedload, and now it's an improvement for Windblown sand. So what we want is we want to predict this threshold theta t. So in these equations, when I go back, you know, we have always this threshold here, and so far always fitted, okay? But now we want to actually predict it. So, and for Windblown sand, what we recently came up with is a very new way of thinking of the threshold. So before I come to that, let me give you a very a brief explanation that we expect the threshold to depend on 2 dimensionless numbers. Why? So because we expect it has to depend on the particle density, grain diameter, fluid density, viscosity, and reduced gravity. And this makes 1, 2, 3, 4, 5 parameters involving 3 units. So it has to depend on 5 minus 3 2-dimensionless numbers. So, and what we now achieved is that we reduced these 2-dimensionless numbers to 1-dimensional number based on very simple and very mild assumptions. So here are the assumptions. In windblown sand, so what we assume now is that Stokes track forces are typically much stronger than form track. Why do we assume that? First of all, in many of the planetary conditions where windblown sand occurs, there is relatively high kinematic viscosity. And that's because the flow density is often quite low. On Mars, the flow density is hundreds of that on Earth. So there it's already, basically the viscosity is relatively high, generally speaking. But in addition, even when the viscosity is not high, we have, from our experience with our simulations, found that Stokes track tends to dominate form track even on Earth. So that is assumption number one. Assumption number two is very similar. We assume a smooth boundary layer flow. So the roughness is proportional to the viscous sublayer scale. Again, this is basically true for all relevant wind-blown sand conditions. So now it comes in assumption number three, which is a bit more tricky. So we are saying the grain trajectories are much larger than the grain size, and this means we can effectively neglect the flow of the wind that occurs very close to the surface. So we can say the boundary conditions just saying at z equals 0, the flow is gone. And at z equals 0 is not the zero height of the flow, but it's the zero height at which particles collide with the bottom. Okay, that's not the same. So it's a bit tricky to say that it's actually 0, but if we say that it's 0, things will simplify a lot. And the fourth condition are what I call scale-free boundary conditions. So when a particle collides with a bed, we assume that the outcome of this collision only depends on the impact velocity, but not on other scales, such as the bed escape velocity scale. And I'll explain in a minute what that means. So if we assume that, and we write down for every single grain the trajectory equations, okay, basically using units of g tilde and EF in the dimensionless trajectory equations, what we find is that these equations, so they will describe when you have an outgoing particle lifting off from the surface, they will link, these equations will link it to the impact velocity. So then if you have a distribution of outgoing velocities, these equations link this distribution to the distribution of impact velocity. And then in addition, you have boundary conditions which link the distribution of impact velocities to the distribution of outgoing velocity. And these boundary conditions do not have another scale involved. What you basically find is that the entire system of equations, including boundary conditions, is determined by two-dimensional parameters, the U star plus and the VS plus. So we will get either, for a given U star plus and VS plus, we will get either no solution or a solution of the system with boundary conditions. And we define the threshold is the interface between solutions and no solutions. And this automatically means that the U star plus is a function of only the VS plus. And the VS plus, there's a different way of writing it via the dimensionless grain size capital D star. So this is just another way of writing the setting velocity square. Square of setting velocity. So what we find is that this U star plus is a function of VS plus or capital D star. And we have reduced the two parameter dependence to a one parameter dependence. And this we can directly check with the simulations. And we find it's really, really nicely obeyed. And then we check it, of course, also with experiments, and it also kind of works. Okay? So for wind-blown sand, what we, the flux model we had before, it's not, it works okay, but not that good. And we empirically found a better flux model that describes the data significantly better than the model which we derived from physics. Okay. And we have also papers on where does this here empirical, but we actually have an explanation for why this shape behaves like this, but I have no time to talk about it. Just mentioning it. So yeah, we improved it and we basically collapsed the data on a very nice behavior for wind-blown sand across many, many different conditions. And here again, experiments. So that's basically the end of my talk. And thank you for your attention.
Thank you, Thomas, for this very interesting presentation. Yeah, so I invite the audience, if you have any questions or comments, maybe feel free to unmute yourself and speak directly, or if you prefer, so you can type your questions in the chat box. In the meantime, I have some questions. Maybe I can ask you. So you approach the problem from the groundwater flow, from the groundwater perspective, right? From the grain scale, but not from the hydrodynamics. So you have a model for drag force, also for the lift force, at the when you write your momentum equations, right?
We don't have no. I don't need to.
You
I
don't
think
need, so
yeah, the model doesn't need that. So the reason why is it that drag doesn't really matter? People really believe, oh, it matters how the drag force exactly behaves and so on. I don't think that's the case, and the reason is kind of simple. So when you have a constant friction coefficient, yeah, you can show very simply in an equilibrium system that the constant friction coefficient is a ratio of average streamwise and vertical forces. So average drag force, and the vertical force is essentially the buoyancy. So if the friction coefficient is indeed a constant, and the buoyancy is kind of it's just a unit, this will fix the average drag force. Whatever the shape of the drag law is, it will always have the same average value. So the shape of the drag law will not have an effect on the global bulk behavior.
Okay, yeah. So all right, so the point is now, because if you say that now the exact form of the drag force is less important, you are considering a one-way coupled system, right? So you are considering the
Please,
effect
I didn't catch the word.
I mean, you are not considering a two-way coupled system, right? So the particle dynamics is not influencing the flow. Do you account
yes,
for
it is.
And which way is that accounted for? How is the flow?
So do you mean in the simulations or in the?
No, in the new model, in new modeling.
So what? So I'm not saying it's not. The equations I look at are the particle phase equations. They are, of course, influenced by the flow. So I don't. In a sense, I also look at the flow being influenced by the particles in the following sense. I'll show you. Namely that this theta t, so basically that you get a law like this. It means that the flow is reduced by momentum transfer from flow to particles to a value theta t. And so what I'm saying is, whatever the mechanism of the momentum transfer from fluid to particles, it will reduce to always approximately the same value, theta t. And the reason for that is the theta t is sort of given by the flow has just to be strong enough to maintain the motion of the particles. Yeah. So even if this theta t means some, even if it means something different, like if for different drag force you would have a different theta mean, that's true. So if you have a different drag law, a different theta mean, and that's exactly what we account for, because that's exactly what this equation, for example, means here. The different drag law will give you a different threshold. So it's accounted for both ways.
Okay. Yeah, some interesting perspective in the fluid particle interaction. Another aspect, this you are more aware of this relaxation behavior of the sediment, but which there are some number of works where the relaxation of the bed matters when you describe the evolution of sedimentary patterns or the formation of dunes and ripples and so on. So do you have any thoughts on that? Because here you merely are looking at equilibrium conditions, right?
So yeah, basically that's what this talk, I have thoughts on that, but in this talk I didn't talk about it.
Yeah.
So, well, what kind of thoughts do you want to know?
I mean, how will they influence now? So you have now these models for predicting the particle transport based on local conditions, right? Both in space and time. So can you use now, I mean, this global quantities, can you use now your models to this time evolution problems, for example?
At the moment, I would say no. But this is the first step towards condition. So usually for time evolution or for the spatial evolution, you need these relaxation lengths or times. And I have actually even published a model in 2013, which I do not trust on that, but we are actually we are working on that right now, and we have a good idea of what is there. So just give you an idea. For example, for the spatial saturation, the most reasonable assumption is that it is simply the proportion to the Hopf length of particles, the average Hopf length. So the average Hopf length we can predict in equilibrium. We're just saying the non-equilibrium scale is proportional to the equilibrium Hopf length. And this gives really good results. So we have done this already in one paper, but we have not really a theory behind it. We have just assumed it. And it worked pretty well.
Thank you, Thomas. Is there any other?
There is one chat. Oh, thanks. No, there isn't.
Thank you. May I just ask one thing? I think it's somehow a continuation of what Amon said, but I was wondering what you think, because you mentioned this is about steady flow conditions. So for example, for wind-blown sands, can we consider the impact of wind gusts, for example, if we consider quasi-steady conditions? Gusts, like a sudden and short period increases and turbulent wind conditions.
So let me clarify first. What we are considering is this long-term time averages, so that we basically really have a logarithmic profile. Because in an atmospheric boundary layer, you may need to average over 10 minutes. I forgot the time, but over a very long time to get a logarithmic profile. However, let's imagine we are looking at shorter times. You could, and I know people have done that, so think of it like a partial, like a quasi-equilibrium over shorter scales, but then the U-star would vary in time. And as long as you, in this quasi-equilibrium state, you still have the same kind of shape of the mean flow velocity, which I don't think is true, but if you had, everything would still work out. So this being said, usually the time dependence is not so much of a worry for us, because when we are looking at the evolution of bad forms, they take a big tune on the planet. They move in time scale of years. So we are not particularly interested in the short-term behavior. So we are more interested in the long-term behavior. So what we would do is we would have our, let's say, 10 minutes mean transport law, and then we would couple it with some kind of variable distribution for the wind behavior over very, very long times, maybe a year or more. And then we would try to make global predictions.
Yeah. Oh, thank you. So you're mainly focusing on the long-term behavior of the transport as well.
Mm-hmm.
Yeah. Thanks.
Maybe I ask another question with hydrodynamic forces. So you say that initially you had some drag force, but then later you modified your model to include also lift forces, right? So
yeah, that's a good point. Yeah, go on.
Yeah. So now, initially, also you in one of these slides, you decompose the particle total force into hydrodynamic component and particle components, right?
This one, right?
I don't know which slide was it. It's one of the beginning slides where you have anyway.
This one, I mean, the slide which is open right now. Can you not see?
This one is for the lift force, yes. Is there an estimate, or maybe you have already done it? Like, what's the ratio or the contribution of these forces, lift forces or drag forces, relative to
Okay. Let me. I was not entirely honest in one point. So when I said in this slide that I fitted this value FL mean to FD mean in to 1.2, this is actually only true for the experiments and crane resolved simulations. The unresolved have lift force, all of them don't use lift force. They have lift force equal to 0 by definition. Okay. So what we for as soon as lift force is equal to 0, this basically becomes just μb minus tangents alpha. But once we have lift forces, how do we know this value 1.2 or whatever we have? This is, we don't really know, but we know what we know is from measurements for a large range of conditions, chip here 1961, 58, that those lift to track ratios are typically close to unity. And for the whole model, we don't need to know the exact behavior of the lift or the exact behavior of the track. What we, for this one, we need is the ratio of mean lift and mean track. Okay. Does this answer your question?
To consider, yeah, it's partly I've answered it, but perhaps maybe I will get back to you with more questions.
Can you try to say, rephrase your question? Or what is your exact question again?
No, my question is like the importance of these drag force models. First of all, you are in the where you are applying these forces in the mobile layer, right? It's not, you are considering particles not too deep in the sediment bed, but also not in the fluid domain. So the density, not the density, but the solid volume fraction is not small, right?
Well, so basically, you know, from the first thing is right, not deep in the bed, basically from the surface to above, but above, everything above.
Yeah, so there is certain, so my general point is that the exact form of this drag and lift forces. So my impression was that they would be important, how they are formulated, but you said that in your modeling, the exact form is less important. So that's your message.
So,
right?
I mean, as long as the form is the shape of the laws is not important for the ratio lift to drag, it's not important. The question is, what does it mean not important? Important in what sense? The only lift doesn't really matter. If lift and drag change the same way in some, then it doesn't really matter what is the one and what is the other. The ratio matters. So that's one point. And also, because you mentioned, do we consider like high above the surface? So what we know from lift forces is that basically you just go above, a little bit above the bed, and they become very quickly 0, right? So the lift force is just a little bit lifted, like 1D above the bed, and the particle basically experience no lift force comparable to the drag force anymore. So this is actually a bit of a physical problem. We have this model that explains everything, but why is lift divided by drag still of order unity? Our reasoning is that when we have ongoing transport, a lot of particles move, that most of them are moving very close to the surface. And potentially when they are moving, they tend to rotate, and this will potentially create other kind of lift forces. And maybe that is what's causing why this value is 1.2 works so well for everything, right? So we don't know why it works so well for everything. We just find it does. And why that would be, it's even possible that what we call lift in this lift divided by drag force ratio is actually not what people would think of lift. Lift means only a force in the normal direction that is not buoyancy. Anything but buoyancy, whatever that could be, right? That doesn't have to be the standard lift, Magnus force or whatever, or shear lift. Doesn't have to be that. Maybe it's something else. It's possible. So we don't know what it is, and we just see the model works very well when we use a constant ratio.
Thanks, Thomas. Thanks for the interesting presentation. Also for your talk. If there is no any more questions, perhaps then we stop the seminar now. But yeah, Thomas, thank you.
Thank you. It was very interesting.
Was it really? I wonder. So few people left. Yeah.
Well,
Okay.
it's just usually it was engaging presentation. Now we are now 1 hour and 15 minutes. Usually people, yeah, they expect like around 45 minutes talk. Then there is